So I'm going to talk mostly about newsfeed and how we rank everybody's stories and try and give them the most interesting content. If we have time, I'll talk a little bit about PYMK and friend suggestions at the end. So we're going to talk about a few things. First, I'm going to start out just give a quick overview of how newsfeed works and what the sort of problem is that we're trying to solve. And I'll talk about how we solve it. And then I'll wrap up and go briefly about some of the friend suggestion work that I did early on in my time at Facebook. So first of all, what's the problem? So newsfeed, you come, presumably most people here have seen it, even if you don't use Facebook. The idea is you come, you get this sort of personalized experience. We take all the things that your friends have done, the pages that you're connected to, all of that content, and try and find the most interesting things, the most relevant ones, the ones that we should put at the top. And from a pure metrics point of view, it's important that we get the right things at the top, just because that's what people see. And you can see, even if you normalize for quality and things like that, all the interaction rates are just way, way higher for the things at the top. It's kind of a standard thing. You want the best content above the fold. There's a bunch of scaling problems. I'm not going to talk too much about the infrastructure, but just to kind of like frame the overall sort of system that we're working in, you've got over 1 billion people coming to Facebook every day. They come, something like 10 times a day, and they read hundreds of billions of stories. So the typical person's reading somewhere in the neighborhood of 100 stories. And of course, in order to figure out which stories to put at the top, we have to rank many, many stories. And so the average person has thousands of stories that we could potentially show them. And so if you do all the math, it means we're ranking trillions of stories. I think it's somewhere in the neighborhood of like 15 trillion stories per day ranked in order to show people their news feeds. So that just implies that we have to not be too sloppy, and we have to make things pretty fast, although we can afford lots of computers, so it's OK. OK, so that's the high-level framing. Let me talk a little bit about how the product works, and then I'm going to jump into the machine learning side of things. So like I said, we're trying to put the best content at the top. Of course, there's this thing where you don't want to put the best content at the top on every single load, right? So if there's some great story of the day, once you've seen it once, you've sort of consumed that content. We don't want to show you that over and over again, even though it may be sort of like the best thing in some objective sense for you. And we also want to have a sort of understandable model of things flowing down the page. And so we came up with this model where every time you come, we'll rank all the new content, put that at the top in some sorted order. Right? So here in this example, I come at 9 a.m. There's 4 new stories. I rank them. I give them some scores. And I'll talk in a minute about how we give them scores. And I just sort them, right? Best things at the top. Now, when I come back an hour later, there's only 2 new stories. Again, each of those gets a score. They get sorted, put them at the top, and so on. I come back at 10 minutes later. There's only 1 new thing that's happened. It's not very good. It has a pretty low score. But still, the model here is put the new things at the top. Right? And this has this nice sort of interpolation between very frequent visitors get an almost chronological feed. You're always seeing the newest thing that's just happening. In the limit, if you're kind of like sitting there hitting refresh, you'll just get 0 or 1 stories on every load. But on the other side, if you only come once a week, if you're a more casual user, we'll take all the stories from the last week, rank all of them, and show you the best things that happened in that entire time period. And so in between, it interpolates nicely. In practice, the model has gotten a little bit more complicated over the years. And mostly, we've just changed the definition of new. Right? So originally, it was like new in some sort of relatively strict sense of, if I came at 10 a.m., it was only the things that happened between 9 and 10. But really, if you're coming to Facebook, anything that you haven't seen is new to you. And so now we're keeping track of what are the things that you've actually seen that we've sort of returned to the client. And so older stories that you haven't seen, they're still new to you. They'll still be eligible to be ranked and put at the top. And so what this looks like is, you come, there's these 7 stories, and maybe you see the first 3. Right? So now we know that you've seen those ones. We're not going to show them again. But those bottom 4 stories D through G, those are still all eligible. And so then when you come back a little bit later, there's some new things that have happened. Right? So there's like story H. That one's brand new. There's also some new information on things that you've seen before. So there's a new comment on story C. And so we're going to re-rank all the things that you haven't seen before, so stories D through G. And then we're going to rank all the new things, and we're going to rank all the things that have kind of new information. There's something new to show you, like the comment on story C. And we'll, again, score all of those, sort them, figure out which ones to put at the top. And then you come and maybe you read the first 2. And you'll notice here that not all the stories get kind of bumped to the top. For whatever reason, this ranking system decided that stories F and G, they weren't quite good enough. We're going to leave them at the bottom. Again, you come back. Everything that you haven't seen gets re-ranked. right? So in this case, stories F and G, you still haven't seen them. They're going to get re-ranked again. And now the system decides, story G is good enough. And this sort of highlights how dynamic and sort of real time the whole thing has to be, right? So in the previous load, that story wasn't good enough to be resurfaced. But now something's changed. Maybe one of your friends has commented on it, or it's gotten a lot of new likes that tells this, the sort of machine learning algorithm that it's better than it originally thought. All these things are happening in real time. And so now on this load, the world has sort of changed in some way, and we decided that story G is the best one to show you at that moment. So you end up with this feed that looks sort of very different. Everything is sort of like moved around on every sort of single page load. So that's the sort of product that we're working in, right? So this is the high-level model. And now the question, of course, is how do we get the scores? How do we decide, the details of what should the order be? Which things should we bump to the top? Stuff like that. And of course, we use lots of machine learning, right? So at Facebook, almost all the products use machine learning in some way. Newsfeed is no exception. And so I'm going to talk a little bit now about how do we actually give the scores, right? So that's kind of the key problem that my team is trying to solving is, there's all these stories. Here's the product. Try and rank all of the new things. How do we actually do that ranking? How do we score the stories? So here's an example. This is a story that might appear in my newsfeed. And this is one of my coworkers. He posted about an earthquake that happened here a couple of years ago. And we want to figure out how good is this story for me, right? So how much will I be interested in this story? And take into account as many things as we can. So Greg is a fairly close friend. I work with him on a pretty regular basis. So we'll try and take that into account. We're going to take into account things like the likes and comments. So this one has 26 likes on it, including one from Mark Zuckerberg. Has a couple of comments. And so we're going to factor all of those things in and try and come up with a single score for this story, which will tell us where it appears in that list of stories. And the main way that we're going to do this is express it as probability predictions for all the different ways that I can interact with that story. Right? So there's a bunch of kind of positive ways that when I see that story, I'll interact with it. I can click on it. I can like it. I can comment on it. I could reshare it. All these different sort of ways for me to do something on that story, which indicates that it was a good story for me. And this is sort of just a classic classification problem. We have lots of labeled data. We're showing people stories all the time, hundreds of billions of them. And then they either scroll past them, those are our negative examples, or they interact with them in some way. And so we can log all that data and do this sort of large-scale machine learning problem. And then it just becomes a mix of feature engineering and then the actual modeling itself. Now at the end, we end up with this probability vector. We have to turn this vector into a single score. And so we'll have some sort of probabilities, which are the output of our machine learning system, and then values. The values is a little bit more of a judgment that we make as a business. We think comments are more valuable than likes. Sort of matches intuition. The heavier weight things are more valuable. And then those details are something that we kind of continue to iterate on through A/B testing, and also through surveys, right? So we ask people to a certain extent, like how important is this story versus this other one, and we can use that to tune the values. But I'm mostly going to focus in this talk on the probability predictions, because that's the machine learning problem. So one of the key things to computing these probabilities is the network structure. And the way that comes into play is through all of the features that we build, right? So I sort of frame this up as this classification problem where we have lots of labeled data. We're trying to predict these probabilities based on the stories that people are seeing and interacting with. And the way that the network comes in is just in the feature vector for each of those, right? So whenever we show you a story, there's a feature vector associated with that, which keeps all this information about you, about the story, about your sort of interactions in the past with people in the story. And it turns out that those network features are some of the most important ones for us to predict, will you like it, will you comment on it, those interactions. And it's really about sort of like, what is your relationship to each of the people, right? So in the example that I showed before, I mentioned that Greg is a close friend of mine. We want to sort of try and model those types of things. We want to get more granular. So the example, my mother, very important person, love my mother. She posts about all kinds of different things. When she posts about the family, or my sister just had a baby, she posts about that. That's a great story for me. On the other hand, she sometimes shares political links. And those I tend not to be as interested in. And I'm sure you all sort of can think of examples like this in your life where there's somebody, and they're important in one dimension, right? Or some type of content that they share is very important, or other types are not. So the other example that I use is my coworkers. They post a lot about things that I'm interested in, machine learning and social networks and this. When they post about their family and their children and dogs and things like that, it's less relevant to me because I engage with them much more in the sort of professional relationship. And so we really want to understand the network at that level of granularity and figure out along each of these edges what sort of is the relationship, how close am I to this person along all the sort of dimensions that we can think of that matter. And so in this example here, there's 3 people. They all see the same story, but they end up with very different weights for that story because they have different relationships with the person who produced it. Different people care, about the content. I guess in this case it's about rain. Some people care more about that than others. There's the relationship with the 4 people who have liked this story. All these things come into play, and they're all captured in the feature vector that we use for the machine learning problem. Cool. So that's the high-level sort of stuff. These are the most important features. Now, how do we actually do the machine learning? So the first thing that we did, and this was until about like a year and a half ago, was we mostly used boosted decision trees. And so the feed ranking team at Facebook went and they built lots of feature extractors. They tried to think of what were the different sort of important dimensions to capture about people and about the stories that are in their newsfeed. And over time, we accumulated this sort of like large mass of features associated with each story and each person. And whenever you saw it, we would log these many, many features. Of course, some of them ended up not being useful, but at the end of the day, we had sort of accumulated, I think, hundreds of thousands of dense features. The average example had a few thousand sort of non-zero features. And so we would then go and try and prune those down to a more manageable set. Because we're training boosted decision trees, we're sort of limited by the number of rows. So how many examples are we training times the number of features, right? That's the like rough memory footprint, and that's the big constraint that we have in training decision trees is just how much memory how big is our data set? And so we would do this sort of iterative process where we would start with all the features. We would train with as many rows as we could fit in our infrastructure. We would then sort of cut off, just keep the most important ones, and then sort of like rinse and repeat, and do this until we got down to the sort of like right trade-off between the number of features and the number of rows. Because of course, as we all know, the more examples that we can train with, the better. And so we wanted to end up with sort of the minimum viable feature set. So we would do this for each of those different events. And so an event, I mean click, like, comment, share, all these different ways that I can interact with stories. And we would get this forest, right? So this output of boosted decision trees is you get a whole bunch of sort of like relatively small decision trees. And the next thing we wanted to do is we would actually not use the kind of direct output of the boosting algorithm. So boosting gives you weights for each of the trees. But we wanted to view these just as feature transformations, right? So we were using the boosted decision tree algorithm just to learn what should the structure of all these trees be, what should the splits be, and things like that. And then we wanted to take that and actually apply a logistic regression on top of that. And the reason that we did this was we want to be able to update all of the sort of the machine learning algorithm in relatively real time, right? So training all the decision trees is very expensive. It's not something that we can kind of have going constantly. And even if we did sort of have it going as fast as we can, just the like collecting data and training the trees on a billion rows or however many we could afford, we would always be some number of hours behind this sort of like real-time data stream that's being produced by people's interactions. On the other hand, there's lots of great algorithms for training logistic regression in real time. You can also do it very easily on the distributed fashion, and so we can train on much more data than we can with the boosted decision trees. And so for all these reasons, we decided that rather than using the sort of direct output of the decision trees, we'll just take these, view them as feature transformations, and then at the end of the day, relearn the weights of all of the leaves using logistic regression. And one way to think about this is that now the trees are really just feature transformations, right? So I've used this boosting decision tree algorithm to learn a set of feature transformations, which take the shape of these decision trees. And then I'm going to relearn the weights of all of the leaves with logistic regression. So the output of each of these trees is just a Boolean for one of the 3 leaves, right? So that was the first thing we did, and this was great in that you can train on all the data, you get relatively real-time updates, and you still get all the power of decision trees, right? This is like a strict generalization over just using the output of the boosting algorithm. So that was up until about a year and a half ago. And then, of course, deep learning and neural networks is all the rage, and we wanted to sort of jump on that train. And so we ended up, taking all of the features that we had built and doing the same sort of thing with neural networks. The big downside with the deep neural networks is that they're very expensive. And so if we're training 10 different deep neural networks for the 10 different events that we're going to predict, it ends up being very computationally expensive. Not to train them so much, that's relatively cheap, but at the runtime when we're predicting all these stories. You'll recall from like early on, I said we're predicting probabilities for somewhere on the order of 10 trillion stories a day. And so we want to make that as efficient as possible. But at the same time, we saw that the deep neural nets on our problem, as in many problems, perform better than the boosted decision trees plus logistic regression that we had before. And so we started first with the sort of deep net classification. And then what we learned was we could actually, there's a lot of correlation between these different events. The stories that are good for me, that I'm interested in, I'm probably going to like them. I'm also going to comment on them. All of those probabilities are correlated. And even if they're not, strictly correlated, at least there's sort of like common things at the initial layers that can be shared, right? There's common information amongst them. And so what we ended up doing was a network structure like this, and then training jointly on all of this sort of like event vector for each of the stories. And so you have the raw features coming in, going through this deep neural network with a handful of layers, and then predicting 3, or actually more than 3 in our case, different events. And now I'm getting most of the power of the deep neural networks. This actually performs almost as well as if I had 10 different independent neural networks, or in some of the cases better because I get some transfer learning, right? There's some events that are very, very rare, and for those ones, it's actually hard to train deep nets on their own. But in this setup, the sort of structures that you learn by predicting like, you can then also apply to these much, much rarer events. And this also has the great benefit that it's relatively computationally cheap, right? If you look at, this is kind of like roughly the shape of the network, and you can see that predicting comment and share is really very, very little additional cost compared to just predicting like, right? It's most of the cost is in the top layers, and those are shared amongst all of them. Cool, so outperform trees. Doing it per event was very expensive. But now we're getting most of the benefit with very, very little cost. So that was we did that about a year ago. But what we really wanted to do was also include, decision trees do some things well that the deep nets don't. We also wanted to include sparse features. We wanted to have ID features, right? So we wanted to have things like what's the user ID or what's the object ID, or in some cases the cross product of the two. And there's lots of other applications where it's clear that sort of large-scale sparse logistic regression works very well. And so we finally sort of converged on this model of the world where we're trying to use sort of the power of all these different machine learning algorithms, and then we combine them at the very end with a sort of like single logistic regression that we can update in real time. And so on the left, you have the decision trees where, again, I'm still training boosted decision trees. I'm viewing all those trees as feature transformations, not necessarily using the boosting weights. For the neural networks, you train the neural networks, as I described in sort of this multitask deep net, but now throw out the last layer, right? So I don't actually need to have the final weights from the last layer to the output node. Instead, I'm going to wire it up directly to this sort of logistic regression layer. And then I can add all of my sparse features, right? So I can take any sort of a sparse logistic regression algorithm, and I'll just throw those sort of on the side. And so this allows you to kind of get the best of all worlds, and now I can add features that are sort of tuned for either the sparse side or the neural nets or the decision trees. And of course, this all works pretty well. And it's relatively computationally cheap, right? So those are the two sort of things. Is it, this performs better than any of those models on their own. We can update it in sort of near real time, and it's performance improvement versus all of the other sort of models. The fan event there towards the bottom, that's one of the ones that it performs really well in this sort of multitask neural network setup because it's quite rare, and the structures that you learn for the other things transfer to that one. Okay, so that's kind of the high-level, quick overview of how we do machine learning and apply it to newsfeed. And now I wanted to talk about one sort of specific network feature that we worked on a couple of years ago called dispersion, and like get sort of like much more into the details of some of the things that we were doing. So dispersion is one of these user affinity features. So I mentioned that user affinity, these sort of like network features are the most important thing for us, trying to understand who are the most important people and in what ways are they important. And simple things like just how often have I interacted with you in the past do pretty well. Those are some of the more important features. But we wanted to ask, what can we get out of the graph structure? Can we sort of come up with some more complicated understanding of the social network? And how well can we do if all we're using is the graph structure, actually? So don't throw out everything about sort of how much I've interacted with you in the past. Like, if I just boil this down to a really simple problem, my input is essentially that graph. How well can I do at figuring out who are the most important people? And so we came up with this concrete task where we have lots of labeled data where people tell us they're married or they're in a relationship or they're engaged to somebody. And we make the sort of reasonable assumption that that's one of the most important people in your life. And then we come up with this task of, given an ego network, so this is an example of an ego network here where there's me, there's the central node is the ego, and then there's all of my friends and which of my friends are connected to each other. And so that's the input, just nodes and edges. And to what extent can we find this sort of one important person, this relationship partner? And so you can think of a few kind of like simple approaches to this. The most obvious one is just embeddedness, or mutual friends, right? So try and find people who I have lots of mutual friends with. I'm like very kind of tightly connected to them in some sense. That's probably an important person. The downside of that is it tends to find these large cliques. So in this example, here's the clique of coworkers. Here's the clique of college classmates. Those are people who I've interacted with a lot on a sort of regular basis, and like they're all friends with each other. And that tends to be what embeddedness picks out. And it misses these kind of important bridging nodes. So here, this person is actually the spouse of the ego in this graph. And if you look at this, you'll notice that it's sort of like this important bridging node. And if you think about this from a sort of intuitive point of view, your spouse or relationship partner doesn't know all of your coworkers and doesn't know all of your college classmates. And so they're not as densely connected to any of these different sort of lobes of the network. But they know a few of your coworkers, and they know a few of your college classmates, and they know some of the people in your family, and they know like one or two of your high school friends. And so we wanted to come up with a way to find those nodes that have kind of like a few different connections to all of the different parts of your network. And so we defined this alternative to embeddedness that we call dispersion, which instead of just mutual friends, it looks at the entire network structure. And basically it says, if you were to take that edge out, so here are two different graphs. If you were to take the edge between V and W out and the two nodes, to what extent would the graph kind of fall apart, right? And so in the case in both of these, the embeddedness is 4. There's 4 mutual friends. In the one on the right, if you take that edge out, it's still sort of this dense clique. And the one on the left, if you take the edge out, it falls apart into 3 different components. And so we define the dispersion to be the sum of the distances between all pairs of mutual neighbors for those 2 people after you delete those 2 nodes, right? And so the intuition here is that my college classmates and my coworkers, the only way in which those 2 groups of people are connected is through me and my spouse, or me and my relationship partner. And of course, that's not strictly true. There's going to be other paths. But the intuition here is, if you take that out, things will sort of like fall apart more than any other node. And the like distance metric that you define doesn't need to be sort of the like geodesic full graph distance. You can actually use a very, very simple definition, which is just that if there's an edge between those 2 people, the distance is 0. And if there's not an edge after you remove those 2, the distance is 1. And then I can just sum up over all pairs of people. After I take that out, are they now more than the 1 or 2 hops away that they were originally? So I'm not going to actually go and do the really complicated like graph problem and find the alternate path through the entire social network. And it turns out actually that this is sort of just an empirical finding. If you normalize it by embeddedness, you end up with the best performance. And so we ended up with this concept of normalized dispersion, where we take, to what extent do these 2 people cause the graph to fall apart if you remove them, and then normalize it by just how many mutual friends do those 2 people have. And so now with that definition, we can go and evaluate it against all kinds of other graph metrics. And we can also evaluate it against some of the behavioral metrics, like how many times have I liked this person's content. So we found 1.3 million Facebook users. They were all in the relationship, engaged, or married. They were sort of normal in some sense, and that they had between 50 and 2,000 friends. They were at least 20 years old, so they weren't 13-year-old girls who were married to their best friend. And for each of them, we ranked by a bunch of different metrics, and we can compare on different kind of performance metrics. How well do these different approaches do at finding the spouse or relationship partner? And so not surprisingly, since I'm here talking about it, Dispersion does much better than embeddedness. So if I look over all the people in that 1.3 million, Dispersion does a little over twice as good. And the metric here is, how often do I just get the right answer? So if I rank all of your friends by whatever metric we're evaluating, how often is the spouse or relationship partner at the top of that list? So it's like the precision at 1, essentially. You can compare these to behavioral metrics. So like co-tagging is just how many times have I been tagged in the same photo, or profile viewing. This is how many times do I go and visit that person's profile. And the graph metric actually does significantly better than either of those as well. I can break this down by married versus in a relationship. And here, sort of, as you might expect, the longer you've been together, the more time there's been for the sort of like network signature to burn in or something, right? So if you're married, on average, you've been in a relationship longer. There have been more opportunities for you to meet the family, meet the high school friends, all of those kinds of things, form those connections. And as a result, in absolute terms, both dispersion and embeddedness do much, much better for people who are married. Co-tagging is sort of a similar story. The longer you're together, the more opportunities there are to be in the same photo. Interestingly, profile viewing goes in the opposite direction. There's less and less sort of new information on your spouse's profile at the longer you're with them. You can also break this down between men and women. And it turns out that the sort of demographic that this algorithm does the best on, for reasons that I don't think we fully understand, is married men, where we get the single right answer about 2/3 of the time. So just this simple network graph algorithm on married men gets the right answer out of those hundreds of possible candidates about 2/3 of the time. Which I think, if you step back and think about it, it's a little bit surprising, right? So I showed you that graph at the very beginning. Is just this like kind of complicated hairball. I think it's like pretty hard to pick out like from just that who would the spouse be. And it turns out that there's enough sort of hidden structure there that we can actually get the right answer over half the time. And this isn't like get the right answer in the top 10. This is get the right answer at position 1 in the graph. Of course, you can use machine learning, and you can combine all these different things. So if we combine all the different graph algorithms that we tried, and embeddedness and dispersion aren't the only two. There's sort of a whole battery of different concepts metrics for graph distance and things like that. There's also a lot of different behavioral things. You combine all of these, you get 71% accuracy. And then the other interesting thing is, we actually don't care as much about just finding your relationship partners. In many cases, you've explicitly declared who you're married to or who you're engaged to or in a relationship with. That's actually less interesting from a practical point of view for Facebook because we already have that data in so many cases. But the assumption here is that if we can find that important person, the same sort of methods give us other important people. And if you go and look at what were the cases that we got wrong, it's often other family members or other sort of important people and that have sort of followed you through life and have many of the sort of like same connections to lots of different parts of your network. You can graph all of these over time, and so you can sort of see what I mentioned of all of these are going up. So embeddedness, dispersion, and photo emitting are going up. They get better and better the longer you're in the relationship. With the exception of profile viewing, goes down over time. At the very beginning of your relationship, you spend lots of time on the profile. Over time, less and less. And then finally, you can do this sort of interesting question of like, what can we say about people transitioning from relationship to single, which is our sort of euphemism for breaking up. And you can look at people for whom we got the right answer versus the wrong answer, right? So people for whom dispersion gave us the relationship partner at position 1, those are the people we got the right answer. Those are correctly predicted versus the incorrectly predicted cases. And then you try and normalize for various things, control for the time since the relationship. And you get this graph where people for whom we got the right answer have a lower probability of breaking up. So I think you can interpret that in a few different ways, but maybe one interpretation is as the sort of like network structure. You have met more of the like high school friends and family and things like that. Is a sign that that it's a more serious relationship, and there's also more support to a certain extent. Cool. So that's dispersion. It's one of the sort of like more interesting features that we worked on as we were trying to make newsfeed better. And finally, I want to spend the last 10 minutes talking about a completely different problem, but one that's very, very applicable to graphs and machine learning, which is people you may know. And so here the task is helping people to find friends on Facebook. Right? So recommendation, super important across lots of different products. Amazon, Netflix, everybody's doing lots of recommendation, trying to suggest, based on your behavior, based on what you've done in the past, here's like products that you would like or movies you would watch. Or in Facebook's case, people you may know. And so like all of these other systems, we can create a lot of value just by increasing the sort of serendipity of the system and making good suggestions of people that you might want to connect to. One of the big differences, I think, between Facebook's problem and things like Amazon or Netflix is it's a little bit less of a collaborative filtering problem, right? Like for us, it's much more about social context. It's not that we're trying to sort of like build a profile of like, do you like Westerns or do you like, romantic comedies, or like you bought this, you'll buy other related things. It's much more, how can we understand the social network and find the people in it based on all the network structure and also behavior that you probably know in real life and that you might want to be friends with. And so what we end up doing is looking mostly at people who are 2 hops away. And so this graph is showing, of all of the friendships that were made on Facebook, how far away were those 2 people when the friendship was made, right? So I become friends with somebody. Before I became friends, what was the path length through the graph? And you'll note here that the y-axis is a log scale. And so the vast, vast majority of all friendships that are made, there's at least one mutual friend. So something like 92% of all friendships on Facebook, there was at least one mutual friend before. And this is important from a practical point of view because it narrows down the scope of our problem significantly. We don't have to search over the entire graph of Facebook to find friend suggestions. Instead, we're just going to focus on those 92%, right? So we're going to try and find people who you have some mutual friend with. They're 2 hops away from you in the graph. Find the best ones of those. So how do we do that? So given a source user, find the best of all the friends of friends, right? So there's my friends, 2 hops away is friends of friends. Figure out which of those people are suggestions. And it's still actually a lot. So if you just think, the average Facebook user has a couple hundred friends and a couple hundred squares, still 40,000. It turns out it's actually more than that because on average your friends have more friends than you. That's not a commentary on people in this room. I'll get back to why that is in a minute. But those are the candidate suggestions. And I think on average there's about 100,000 friends of friends for people. And the most active users who have up to 5,000 friends have many more than that. And so the first thing we'll do, of course, we're going to use the social network. The obvious sort of feature of embeddedness is an important one. So this graph is showing the number of, the probability of a new friendship as a function of how many friends you have in common. It goes up very, very fast. I think, again, the y-axis is a log scale. And so if you have hundreds of mutual friends, you're much, much more likely to become friends with that person than if you only have one mutual friend, which kind of makes sense. Those 100,000 people, most of them you only have one mutual friend with. A very small number you have hundreds of mutual friends with. And we're going to tend to suggest the people on that side of the spectrum. Of course, the graph is much, much more complicated than just like nodes and edges. And this is one of the key learnings from this work was that you shouldn't just think about it as this sort of simple, there's nodes and there's edges. All of those edges actually have a ton of metadata associated with them. So there's the direction of the edge, who friended whom. There's the timestamp on the edge, when was it created. There's how many interactions were there along the edge. So how often do I like your content and interact with you on Messenger. All these different things end up being kind of critical to this problem. It turns out one of the most important features is actually how old the edges are. And so the intuition here is, if you've been on Facebook for a long time, you have all these friends from past sort of like parts of your life. I have my high school friends. And I still want to be friends with those people. At the same time, it's not that likely that I'm going to now become friends with somebody who I was friends with in high school, right? I've sort of like moved on from that part of my life. Those people live somewhere far away. Whoever they're becoming friends with or whoever they're friends with in their sort of new life, I have no connection to those people. So even if I had a bunch of sort of mutual friends with somebody who lived back in my hometown, for instance, That's probably not a good suggestion because all of the edges there are sort of new. Whereas the person that I just became friends with today, that person, that's kind of the direction that my network is growing right now. Their friends are a good suggestion. And so we want to take things like that into account and come up with sort of like weighted mutual friends. And so then to make predictions, we'll consider all of my friends of friends. For each pair, we're going to generate lots of features again. And the biggest ones are these kind of like various weightings of mutual friends. So the simplest one is just total number of mutual friends. But then we have time discounted mutual friends where we weight all of the edges according to kind of how old they are. And like focus on new mutual friends especially. We're then also, of course, going to incorporate any other features we can think of about me and about the person that's the sort of candidate. And again, we'll put all this into a machine learning to try and predict the probability that I'll friend somebody should I see them as a suggestion. And again, we'll use some boosted decision trees. So we have our feature vector. I have 5 mutual friends. My gender is male. My age is 23. The other person, et cetera, et cetera. And we get some sort of probability of friendship out of this. Again, the network features, this is really the key to the whole sort of friend suggestions. And it's thinking about the graph not as just nodes and edges, but as this much sort of richer data where the edges all have directions, there's different types of edges, there's different weights, and really kind of viewing the graph more like the one on the right than just there's circles and dots and lines. And yeah, so the 3 most important features, it turns out, time discounted mutual friends is number 1. Just sort of the country and age, so what part of Facebook are you in? And then it turns out actually, and this is one of the interesting things, this is not very discriminative, but it's sort of important for the generative part of probability prediction is just how many friends I already have is a pretty important feature for predicting, just am I an avid sort of Facebook user making lots of friends or not? And obviously that doesn't help to distinguish between all the suggestions, but it helps to calibrate sort of the overall probabilities. And now finally, so I mentioned that on average your friends have more friends than you. And this is this kind of like fun friendship paradox that I want to spend just 1 minute talking about, where if you look at this graph, this is the degree, so the number of friends that everybody on Facebook has, and then the y-axis is the average degree of your friends. So until you get up to around 700, your friends have more friends than you. And the reason this is, it's actually kind of a property of almost all networks, and it's that if I only have 1 friend, I only get averaged into one person's like average friend count of friends. If I have 1,000 friends, I get averaged in 1,000 times. And so really the average degree of my friends is more like the second moment of the graph, not just the average degree. And so that's why for almost everybody, their friends have more friends than them. Oh, it's kind of a fun paradox. Anyhow, we end up ranking lots and lots of suggestions. And the last thing is so doing this is expensive. There's hundreds of thousands of potential candidates. The nice thing about this problem is that unlike the newsfeed problem, the graph isn't changing very quickly, right? So it's not evolving super fast. And that means that we can cache the results. And we can just figure out who are the top 100 suggestions. Again, though, we don't want to just show the top 2 every single time I load the page. And so we're going to just keep track of the impression count. And it turns out it follows this very nice sort of like 1/x curve. And so for any specific friend suggestion, roughly the probability that I'll become friends with that person is some sort of like absolute quality divided by the number of times that I've seen it. And so in this sort of like real-time system, you have the cached sort of like top 100, and then you're just re-ranking the top 100 according to the sort of like expensive score that was produced like offline using all those like mutual friend features. And then this one sort of impression score of how many times have I seen it. So here there's 4 suggestions, and then as the impression counts get incremented, they all get re-ranked. And there's just some very simple model that combines the original CTR prediction with the number of impressions to come up with that re-ranking. All right, this all worked very well. So here's the CTR as we launched it, and you can kind of guess where we shipped the new system. There was an older system that didn't use all this fancy machine learning, and the new system allowed us, because we had good probability predictions, we were able to just cut impressions. So if we think there just aren't any good suggestions, we just won't show you PYMK, we'll show you something else. And the suggestions that we did show you were better. And so our CTR was up by 130% when we first launched sort of the system that I've described here versus what we had before, which was sort of a more heuristic approach. And that's it.